Hello and welcome. Here we are in lecture 11. We're going to continue where we left off last time, talking more about our very informal, very practical guided tour of functional programming. Rather than emphasizing rigor in theory, we're really emphasizing on what can we do to make our hard design generators easier to write, easier to read, and hopefully more correct and such. So, in our first lecture last Wednesday on functional programming, we really kind of emphasized things that are like map, right? That is, we have some collection of objects, and we have a new collection that comes out the other end. It's the same size, just we've applied a function to it. Or perhaps with for each, we applied a function to it and didn't even keep the result, right? Today, we're going to go a little bit of a different direction. Instead of having, we're going to have a collection of objects coming in, we're going to apply a function to each element, but in this case, we're looking to aggregate them, right? So if we have many elements, we want to somehow reduce them down to a single element, right? And so that's what today's functional programming is about how to, instead of mapping one-to-one, how can we reduce? So let's get right to it. So in particular in Scala, or in functional programming in general, the operators we're referring to are called reduce and fold. And along the way, we'll cover some details about some of these type signatures are kind of seeing floating by in Scala. I think now is a great time to talk about because there'll probably be occasion looking up documentation. This will help make it easier to access that. And some other things to consider along the way. And we'll actually conclude with a lot of case studies taking examples from the prior 2 or 3 weeks and showing I can redo a lot of these functional programming. So, before we kind of kept teasing, oh, wait, we'll do things nicer in functional programming. Well, now is that time. We're hoping to do things nicer. Okay, so let's go ahead and load up our notebook. And so as I said, right, last time we were applying things one-to-one, right? For every input element in the collection, applied a function to it, and now we had an output element. And that's what we were worried about doing, right? And in the case with reduce and fold, now we want to combine and collapse these things, right? And there's kind of multiple things to ask when you ask this question, right? Is not only are we trying to collapse these things or combine them, but what happens in the kind of corner case? What if somebody wants to collapse only one thing or 0 things? What should I do? And so that's going to be kind of part of these corner cases we're thinking about today about how we handle these things. So first off is reduce, right? So what is reduce? Well, you give it a binary operator, and keep applying it to the elements until we're left with just one thing, right? So, for example, if we have this sequence to play with, and we want to reduce it, we of course can, say reduce. We can use those placeholders we talked about last time. These underscores, of course, act as, substitute the variables, and so each use substitutes for a different variable, right? So for reduce, we're actually going to need to have 2 arguments. So maybe perhaps you should think of this way first. It's kind of more verbose way. I've taken 2 arguments, adding them together. As opposed to, we can, in this case, use the placeholder syntax. Great. So we go ahead and run this little snippet. Yeah, okay, we reduce this down by adding them. If we want to kind of get clever about this, we can say, hey, you know what? What if we square every element, multiply it by itself, and then here we're using the more verbose syntax rather than the placeholders. And then if I just take squares and then apply reduce to them with the addition, right? And okay, so that basically is now a sum of squares, right? We're adding up squares, right? And, we could just as well do this right now. Notice here, one of the reasons why we could not use the placeholder syntax is we need I twice, right? So if I was to do this, if I tried to do this, it's going to break, right? If I tried to do just like this, the reason why is because each use of a placeholder advances kind of the next argument, right? So in this case, you actually only need the same argument twice. Can't really do that. So you should actually just write out the thing more verbosely, which is fine. Cool. Questions so far? Great. Okay, so reduce seems pretty handy, right? This can solve a lot of problems. So let's go ahead and try it out, right? So remember, we built an arbiter. One of the parts of our arbiter was we had a number of things going on in our arbiter, right? But so we covered this in the last lecture. And remember, our arbiter is kind of basically a collection of things being fed into very correctly, intelligently into the priority encoder, and then kind of filtering the thing out the other end with a mux. And a lot of what's going on here is kind of making various connections. And really what we're doing, remember, is kind of collecting things, right? We need to have all the valids in the single vec. We need to have all the bits in the, a vec of, buses, so to speak. And we kind of use this for loop to kind of gather these things together. So this for loop was kind of acting as a gather for us. And then we do all this other stuff. So if you remember from the last lecture, we said, okay, great. We can go in and use maps to do a lot of those gathers, right? So instead of having a for loop to gather those things, we can just map them. And then for the other gather, for in bits, we did in bits. We not only can do the gather of a map, we can actually just replace it in the place it's used. So we can even have, remove the need for an entire variable. And then there was this need to make a connection. And so that's a, situation where we don't really care about the output. We care about the side effect, right? And so that was one that made sense last time to use a for each, right? We did that. Okay, so then that's all from last time, map and for each. But there was one thing left, right? One thing left was we had this, we had to take our invalids, and then we had to turn them into UN and do an OR reduction, right? So the fact that it's called an OR reduction perhaps should have been a good hint that we could have used a reduced, right? So that's what we did. So we have, a bus of single bit wires, or a vector of single bit wires, and we just want to know if any one of them is true, right? So we're going to reduce them together using the OR operator, right? And so you can see here, this is not so much a line count reduction, it's a 1 for 1, but perhaps this is a, less typecasting, just more kind of direct, it's more clear what you're trying to do, right? Basically you have these things and you're just trying to reduce them together. Cool. Okay, some questions in chat, and I'll go ahead and answer those. So yeah, what is this OR R? So that is what's called an OR reduction. So it's only available on uints, which is why this vec had to be cast to a uint. And it takes all of the bits and does an OR on them, right? And combines them by OR. So it's basically kind of like a bitwise reduce built into chisel, right? So in some ways, maybe the .OR is arguably better because it's using standard library components, et cetera, et cetera, et cetera. There's also an AND R and an XOR R. And these are just referred to as reductions. Interestingly, they come up just enough in hardware design where people actually put them in languages. So actually in Chisel, you can just do, in Verilog, you can just do a single vertical bar to do an OR reduction, and then on like a variable over here. And so it's like weird to have an OR bar without something on the left, but it actually does as an OR reduction. So it comes up in hardware design where a lot of times you want to know, is any one of these bits true, right? And interestingly, when you think about what that means mathematically, right? Okay, if any bit is, so okay, if I have, n bits coming in, do an OR reduction, gets down to 1 bit, that 1 bit's going to be true if any one of his input bits is true, and it's only going to be 0, the output bit, if all of them are 0, right? So basically you can imagine you could actually just turn an OR reduction into comparison against 0, right? Where if it does not equal 0, then it's a 1. If it does equal 0, it's a 0. But mathematically, it's kind of to figure out a reduction, right? Cool. Great questions. Oh, yeah. So the TA is pointing out in the chat that you can also... okay, I'm trying to imagine... Okay, yeah, the TA's parsing through the code the TA suggested. Oh, that's an interesting use. So yeah, one of the things you can see with functional programming is you can often chain together things. So in the chat, the TA has suggested if you want to do an exponent, you could, for example, fill a sequence of the variables you want to do with the exponent and then do a reduce, right? So yeah, there's all sorts of clever ways you kind of can combine things. It's kind of fun is these are composable tools, right? You can kind of take the output of one, feed into the next one, et cetera, et cetera. Can you repeat that? I think there was a comment someone said, and I think I had my audio set up wrong, but I think it's fixed now. Yes. Yeah. And so if I go back a slide, maybe I should tell you this now so I don't forget later. Um, for things like these special case reductions, uh, Scala has nice things already available. So I can, instead of saying, L reduce in that case, I can just say dot sum, and that's there, right? And there's also a dot product. And so it's kind of a really fun language where it has a lot of stuff like built in. Occasionally, you maybe not even think to look for things. Like you're so used to writing stuff yourself, you wouldn't even think to look for it in a library. This is a classic challenge for a lot of languages where there's something in a language, maybe it's an idiom, maybe it's a library feature that people aren't thinking to use, and how do you get people to use it? Well, there's kind of two ways to get people to use it, and they're both available with Scala, right? So one is that your IDE will actually have some sort of plugin running in the background saying like, oh, look, you did this thing, and this is, internally being pattern matched in some sort of database and saying, you know what, you could use this one built-in feature to do that, like, thing much simpler. And you're like, oh, that's cool. Thank you, tool. The other way is you actually can go ahead and get feedback. Now, if you get feedback from somebody who's an expert developer in the community, you can also sometimes read a blog. So actually on our course homepage, under the references for Scala, we have a link to this developer's Pavel's blog post where he lists out many things that people do in Scala, not being aware of what's available in the library. And these are things where the code he's kind of criticizing or suggesting you do differently isn't functionally wrong. It's just, oh wait, instead of doing not signed and on dot that is empty, I could do non-empty, right? And so there's a lot of things that are kind of built into the language you wouldn't necessarily know about. And if you want to skim through that blog post, I recommend it. It's kind of cool. You can see a lot of that helpful stuff in there. And then, so I'm going to return back to the chat. There's quite a few follow-ups in the chat. So the question is, when I do something like reduce, what's the topology, right? Am I going to get like a, logarithmic depth, perfectly balanced tree? No. You're actually going to get a linear application of this operator, right? Now, inferior for reduce, there's some flexibility for the tools to kind of do it in their own desired order. But in practice, you're going to get a linear number of things. So if I have n things, it's going to apply reduce n minus 1 times, because reduce requires 2 things to apply to. So it's going to be the, sum so far, and then the next element, right? This is going to be a, linear unbalanced thing, right? And so, yeah, for hardware design, that may not be ideal in some cases. Maybe you do really want to manually control the topology yourself to get a tree, which will be, more hardware, potentially, or at least shallower depth, right? You want to rearrange things. And so, yes, good question. It's going to be, that single unbalanced linear sequence. And then the questions are, we're talking about this is the best way to do exponents with chisel. So remember, when you're trying to exponentiate, we're trying to, apply multiplication some arbitrary number of times. The arbitrariness needs to come at hardware generation time. Of course, when hardware actually exists, we want to actually, it needs to know how many multipliers to put in there. So we saw an example of, not saw it right now on the screen, but, in the chat, we're talking about what if you could, do it with, the reduce after doing a seek.fill. I personally, if I was trying to do this, I would probably use a write a recursive function, even though it's perhaps more verbose way of doing this. But that way you can maybe label it like exp, so that way people know that's the kind of understand what you're trying to do. It's kind of a way. Sometimes it's nice to actually do the more verbose way because it gives you a chance to label things. So I can say, hey, this is, exp, exp for exponent, right? So you can kind of label and say, I'm trying to do that. And that when someone reads your code and it's the exp, they suspect it's probably a bit of an exponent. They don't, maybe they can read the function. Oh yeah, it's exponent. They keep going, right? And so, there's no always hard and fast rules, right? Sometimes when it comes to readability, try it one way, try it the other way, see what you think, go through code review, see what someone else thinks, etc. Cool. Okay, and then more chat. Okay. So the question is, when I mentioned this, being unbalanced for this topology, reductions like this in this linear sequence, will the tools go in and optimize it? It depends on which tool under which circumstances, but actually maybe not. So depending on the operation you're doing, it may be semantically inappropriate for the tools to do this, right? So for example, if I'm doing addition and I'm not growing the bit widths, rearranging, a linear unbalanced thing into a tree actually is a different semantic behavior, right? Because now I'm performing accumulation in a different order, and such, it's not going to be the same. However, for example, if these were like binary operations where there's no possibility of losing stuff, actually the tools could do this, right? And I think not so much Fertile, but the downstream CAD tools, I'm sure would optimize the heck out of it. And so it's one of these things where, don't worry about performance until you have to, right? So in this case, the linear thing versus the tree, the two topology choices, they're actually similar amounts of hardware, right? It's just a question of how it's arranged for critical path concerns, right? And so until you have a critical path problem, I wouldn't worry about it. In this course, we don't really push through downstream CAD tools, so critical paths don't really come up, so I wouldn't worry about doing the tree for now. But yeah, you should be aware that tree is going to be more efficient. If you dig around the Chisel standard library, you can see some places where they really wanted a tree. Actually, I believe the OR reduction, other than comparing to zeros from the other things in the standard library, you actually see them doing a tree, and they actually do as a kind of recursion in having the number of elements each time. And it's not impossible, but it's more complicated than you expected first. Cool. Wow, a lot going on. But good. I'm happy to have the conversations. This is great. Cool. Okay, so this is mostly what we did last time. We just have this extra line using reduce. Okay, what else can we do? Well, so reduce is pretty cool, but it requires two things, right? It requires, two elements, then combines them to make one element. And the question is, well, what should a reduce return if you have zero elements, right? It's kind of its, default behavior. Or what happens if I have elements and the output type I want from our reduction is different than input element type, right? So you can imagine when you're doing reduce, you combine two elements, you have a new element that needs to be the same type of another element, so we can keep applying the same binary operation that, takes two elements of some type, produces another element of that type. What if you want to take in two elements of a certain type and produce potentially a different output type, right? Perhaps maybe you're taking elements in individually and you want to produce the output type is going to be a list of elements, right? That wouldn't be possible for reduce, right? So enter fold, or I should say more specifically, fold left. So yes, because it's called fold left, there's also a fold right. And for now, you can maybe slightly ignore the details of what does it mean left versus right. We'll come back to that in a second. But practically, you're going to use fold left most of the time. And actually, this is a more general operator. So you can actually basically use fold left to implement reduce functionally. But there's some reasons why you may prefer to use reduce in practice. One of them just being it's very clear and easier to write. So let's look at some cases here. So for example, let's start off with a handy sequence and say, you know what? Why don't we, add them up, right? So the thing about fold left is we need to give it not just a binary operator, but also an initial element, right? And so this initial element, remember, can be potentially a different type than input elements, right? So this is more like the initial accumulation, so to speak, or result, and then this function is going to take in that type, an element, and then produce something else, right? And so here we're doing fold left for summing, right? So, okay, we're going to have the kind of total so far, and then we're given an element, and then we're going to add them together. So I use this kind of very verbose names to kind of keep track of what's going on. And you'll notice we give it this initial result first, and then we give it the function. We can use the placeholder syntax, no problem. And so yeah, if we go ahead and run this, these are three different ways of doing the sum. Also, of course, I should have that one. Maybe can't do the without the dot. Okay, and then what about instead of summing? What if I want to do like a max, for example? Well, okay, if I want to implement max, I can define a function, right? Okay, max so far and x, okay, either return to max these two things. And then I can apply this function, right? So you can name things and then, I'll go ahead and apply them to folding left on 0. Okay, so this is max the hard way, right? What's max the easy way? Well, that's max the easy way. But there we have it. Cool. Okay. In the next slide, we'll actually show you, I think, the directions. But for now, I'll pause for any questions on this part so far. Okay. So as I said, there's a fold left and a fold right. What does that mean? Well, honestly, I get confused with left and right because, you know, when I write out my elements, am I putting index 0 on the left or right? And also fold left, if, for example, if you put element 0 on the left, is going left to right. So it's actually going right, but starting on the left. The way I think of it, remember it, fold left is increasing in sequence order, right? So 0, 1, 2, 3. Fold right is decreasing in sequence order. And in this case, I've, you know, laid it out such that, you know, it's consistent ordering for the indices, but, you know, you can see left going from left to right or from right to left. But kind of way to think of it is, yeah, fold left is increasing sequence order and fold right is decreasing sequence order is the way I like to think of it. But either way, you can kind of see what's happening, right? We're taking in some sort of initial thing, an element, and we're producing a new thing, and that's being used to produce it. And so additionally, in addition to, okay, so cool. Cool, okay, so kind of remember what we're covering here. We just saw an example where we had two sets of arguments being given to an operation, right? For example, we go back to fold. We see that, right, there's two sets of arguments. So what is that? For those of you who haven't seen that before, that's something called currying. And this is, you know, available in our languages. It's also available in Scala. So basically, you know, instead of having just a single argument list to a function, we can break it up into two or more, right? And so the reason why you might want to do this is you may not apply all the arguments at once, right? And the reason why it's beneficial to have these kind of partially applied arguments is when you want to do functional programming. So for example, you know, okay, yes, I can do a sum function, no problem. What about plus x function? So it's going to be given an x. So that's what this function does is it's going to, this is f, that type is still actually going to be a function, right? So because we applied one argument, okay, we've taken care of this set of arguments. There's still another argument left, right? So this is still a function that takes in an int and returns an int. And it's just this particular, you know, bound instance of plus x with that argument bound to 1, it's going to add 1 to everything, right? So, you know, if I have f and I, you know, add 1 to it, okay, that's plus x. You know, if I can call both arguments directly. It's the same thing. It's going to be 3, right? And so, for example, what's cool about this is I now can, you know, create a function, right? So it's almost like a function generator in a way, right? Where, let's say, for example, I want to map it onto a sequence. And so I'm basically preloading in the 10 into the first portion. So this operation is going to produce a function that takes an int and adds 10 to it, right? Because it's going to go ahead and do this and put the 10 in here and do that. So it's going to return a function that takes in an int, produces an int. So map, you know, is going to need a function that takes in an int, produces an int. So it's going to go ahead and apply that. And of course, we get 10 added into all of these. Cool. Yeah, we can keep talking about. Okay, so, oh, and the question is about the syntax, like, how would I know to do this? I don't know if you necessarily would know, but now you know, hopefully. I'm not like a language person. I can't tell you about the implications of certain syntactic choices, but it does kind of make sense, right? They're still kind of in the same place you expect arguments to go. It's just, is it one group of parentheses or perhaps multiple groups of parentheses? And when you apply them only partially, you're going left to right. What is the underscore used for right here? That's just kind of indicating we want the to bind to it. Most times you're going to do a partial function. You actually won't need that. You can just do it like this, and that'll be just fine. However, right here, if I don't include that, it's going to complain, right? Because it doesn't know. This is not a full evaluation. This is just a partial evaluation. So you kind of need to tell it, hey, you know what? This is that placeholder syntax. So this is going to need another argument, and so that's kind of what you're telling it. This is really kind of a special case. Really, in the common case, you're going to be doing something like this, in which case you won't need to do that because it's already kind of from the context going to know it needs to, and knows it needs to make a function. But yeah, great question. When I was preparing these slides, I was like, oh, why do I need this? And then, oh, that's right. And so yeah, it's a little surprising, but I think it makes sense if you think about it, like, oh wait, the partial function is not fully applied, and it kind of indicates the function. So yeah, that's kind of what that's for. But yeah, this scenario is more rare, right? You're going to be, if you're doing one of these kind of create functions to do partial application, you're probably going to be instantiating it inside of the context of a functional operator. Cool. So now that we've talked about the currying, I think now we actually can go full circle and look at the function signatures for these functional programming operators. So as I mentioned before, things like map, fold left, for each, these aren't language keywords built into the language. These are methods implemented on the collections we were using, right? And so the behavior of them is very standardized because there's it's inherited via a trait, but technically these are methods implemented on these collections rather than something built into the language, right? And so what does it look like? Well, how it looks is that you here's one of these signatures taken straight out of the Scala doc for the language. For example, here we're looking at for sequence, what does map do? Well, map, and you apply it to a sequence, right? 1 to 1, you're gonna get another sequence out. And what's interesting is the types here, right? So it's gonna take in a function, you're calling this on the collection, right? So you say l.map or lmap. So now it's the function you're giving it. Its arguments are in parentheses, right? So it's taking an argument of type A, which is the type of this seq in the first place. And then it's going to return an element of type B, right? And that's what this templating is here. So now this map operation is actually kind of in a way templated by type for the output. So A and B can be the same type, but actually also can be different types, right? And we've done this in our examples, right? When we had a list, a seq of Scala ints, and we, map them to chisel uints, right? Those were different types for A and B. No problem. That's normal for map, right? And so let's say, for example, you forgot about map, and you had to go look it up. Here you go. Now, more common, which is me all the time, you forget the exact order of the operations or signature for fold left or something, right? So, okay, so for fold left, once again, two different types. The original collection is of type A, or I should say sequence or collection of type A, and now we're returning a single element of type B. Okay, so in that case, what do we do? We need that initial element, in this case z, perhaps for 0 or whatever, and then the operation is going to take two arguments, right? The accumulation or results so far, and then an element from the thing, and then of course it's going to apply this binary operator and get a new element and then output type, and it's going to continue applying it, right? And so, of course, remember the whole niceness of fold is that if I call fold on empty collection, I'm just getting this back, right? Cool. And so, yeah, this is helpful. Where I said if you forget and look things up in the Scala doc, here's kind of the way how to read these signatures. So hopefully that helps. Cool. Other questions? Okay, so let's keep going. So if you're doing math at home, you're saying, wait a second, we talked about there's a fold left and a fold right. Is there a fold? Wait, there's a reduce. Is there reduce left? Actually, all 6 exist, right? So there's reduce, reduce left, reduce right, fold, fold left, fold right. All 6 exist. I don't think you necessarily want to do all 6. So what's going on? Well, if there's no direction specified in the name, technically there's some leeway for the language, compiler, library, etc. to choose how it's done. In practice, I believe, by default, reduce is usually reduce left and fold is usually fold left. But that's kind of one thing. Now, like I said, for which ones are you actually going to use? Fold left is very common. It's the most versatile. You can, basically do what reduce can do with fold left. However, sometimes I use reduce, right? Why is it nice to use reduce? It's a little bit simpler. We don't have to worry about that 0 element. The type signature is a little easier. It's easier to kind of do it with the placeholder syntax in many cases. And so kind of how do I tend to use these? I tend to use reduce. Don't really care about the order. Just reduce when I want to combine things. And then fold left. Actually, it's not so much about combining. It's more about like basically doing things in deliberate order. Because if you think about it in a way, fold left is kind of like you're just looping over your collection, right? So earlier when I pitched functional programming, I said that you can use these operators that kind of capture common patterns. A common pattern seen just a second that fold left kind of captures, this pattern of having a for loop iterating over elements one by one in order and having some sort of accumulation. That's basically fold left, right? And so fold left lets you kind of do that in a very deliberate order. In this case, fold left is ascending in sequence order. So, 0, 1, 2, 3. So it's kind of a nice map for that. And so most often in the designs, you're going to use fold left or reduce. And I just find fold left a little more complicated, a little more cumbersome. So if I can get by with reduce, I'll use reduce. But there's also fold right and reduce right. So what are those for? Well, those are most helpful for doing things in reverse order. Like there's sometimes the reason why you don't want to go 0, 1, 2, 3. You want to go from, n minus 1, n minus 2, etc. So that's what fold right and reduce right are for. Now, if you forget that or don't remember to do that, you also can call dot reverse on a collection to reverse the order initially and then call fold left, right? So these are all possibilities. And then, as pointed out in chat, they're like, oh, wait, I think, in Haskell, and this is, I'm pretty sure true for functional programming in general, how you have, left versus right is helpful for dealing with infinite sequences, and perhaps having some sort of continuation or yield or something like that, or streams. Yes, totally true. When designing hardware, because this needs to turn into a physical thing, we tend not to have streams, right? Because we need to know what we're talking about, right? But yes, I think that's definitely true. So as I said, this is a practical architect's guide to functional programming, not a PL person's, formality. But yes, I'm sure that's a very useful example for why you'd want this. But for me, if you have hardware where when you're generating it, you're afraid to have all of the stuff visible in scope, it's a sign your hardware might be unbuildable. But yeah, great suggestion. Cool. Okay, so now we have a bunch of case studies. So remember earlier we did reduce, and that's the example I just described just a second ago, right? Maybe I'll uncomment to make it extra clear, right? So you want to simply add all things together. Well, what we learned earlier in this course, just 2 weeks ago, what do? Well, we use the var, which we try to avoid when we can, as kind of our starting point, and then we kept adding on to it, right? The total so far is equal to that. And so we kept overwriting it and adding on to it, right? And then that was it, right? And this got the job done. It is hopefully not super confusing what's going on here. But yeah, I mean, it's 4 lines, right? I need to declare the var, I need to iterate, I need to do final connection. So yeah, if you want to look at the Verilog code, sure. The Verilog code for this, not too crazy. That's what we did earlier in the quarter. Now, if I did this with functional programming, I can do this. And yeah, it's 1 line. Hopefully calling reduce in this manner is not super confusing. I'm actually now curious if I can get by with .sum. I think I probably can. I think it might be inherited. Let's find out. Nope, maybe not. Yeah, chisel not define .sum. Oops. But fortunately, it does define reduce. So this actually is calling reduce on a vec, right? So vec implements that reduce method, and we can do that. Awesome. Cool. So yeah, here's an example where now that we know about functional programming, I would argue that this is perhaps better code, right? It's easier to write, it's shorter, but I think the intention is not super surprising, right? Where someone can read this and figure it out, it just takes a little bit more time to process, right? They got to understand, okay, there's some sort of initial thing, I'm iterating, and then I'm adding them up and connecting. Now it's all at once, right? I'm just reducing all these things together and connecting it. Cool. So yeah, this is, I think, in this case, I would argue functional programming is a definite thumbs up. This is making things easier. The only person you're hindering of readability in this case, I would argue, is someone that perhaps is not familiar with functional programming, which is worth considering. But hopefully, eventually, with Chiz, we'll get them on board, and they'll be okay with that. All right. Another thing we did earlier in the quarter, even earlier than we did the reduction, was this like a pipe or delay in or shift register, we want to call it, where we had n registers in sequence, one feeding into the next, right? So if we did that before, how do we do that? Well, we did it a few ways. We did it with a for loop. We also did it with a recursion. So just for sake of argument, here's the recursive version. So we have this helper function, right? And basically, it's going to iterate n times and knows how to do kind of a base case. And when it's recursing, it's going to, take the last connection, make that the input of a new register, and then remember the output of this register, and then use that to kind of pass it on to the next call of helper, right? And so yeah, we had to write this recursive function and do this. And once again, someone wants to take a second to read this, they can read it, pause, perhaps give it a better name than helper. You can help them along. But there's still some cognitive load to process this, right? Alternatively, now if we do a functional program, well, maybe we'll go ahead and run this first. And okay, yes, you can see, maybe we'll do 3 registers. Cool. Okay, so they're feeding in together. Now if we did this with functional programming, we get basically the same result, but what do we do? This is actually an interesting case in this one, because even though we have a collection of things, the collection of things actually isn't important. What's important is how many of them there are, right? So you can see, for example, that here we have, we want to do n things. Okay, we're going to fold left. We're going to start with io.in. So one of the things nice about fold left compared to reduce is it handles, 0 almost very gracefully. And what do we do? Well, we're given the, result so far and then the current element. And well, if we actually are calling this operator, we're going to go ahead and do regnext on it. And so, yeah, this is there. To be fully honest, I don't even have to do this for years. Fold left takes a little bit of time for me to parse it. And so I'm not going to say this is as clear of a slam dunk. This is a lot better, but we did it with functional programming, right? So check, we did it. I think this class is a great opportunity for those of you to try things out. Try to go immutable as much as you can and not use var. Try to really embrace functional programming, and don't be afraid to deliberately go too far and realize, oh wait, that actually was confusing, or that actually was hard to read, or whatever. And then you can kind of get appreciation for what's the right amount. And so I believe these features, when used appropriately, can be really powerful, right? And so yeah, like I said, it's a fun class. Don't be afraid to maybe perhaps deliberately overdo it to see what too far looks like, and then reel it back in, right? And so yeah, here we have this line. It's a single functional operator. It's not like me, I'm chaining together many things, but I find the folds are always a little bit more cognitively demanding than like a map. Like a map, oh yeah, it's so clear. Input, output, that makes sense. Fold left, you gotta kind of appreciate the initial thing, and then this operator, and I always forget it's the accumulation first and the current element second. That's why I have to look at the type signature in the Scala docs. But there we have it. Cool. Questions so far? All right, so then this next operator is actually more like the map for each category. So what does this one do? It's called zip with index. So even though we're mapping things, sometimes you have a collection where there's indices and you actually don't want to lose information. And so sometimes you might find some situation where you could do this with map, but you actually prefer to do a for loop because you want that index, that I to play with. Well, if that's something situation you're in and you want to do things in the functional space, there's something called zip with index. So it's going to take your input collection, take the indices, and then pair them together. So it's like doing zip. So as the name implies, it's zipping with the index, right? So you see my little code examples here. If I have a sequence and then I zip that with 0 until the size, I will get the exact same output as zip with index, right? So this is basically kind of a shorthand for that. Cool, and here's some examples using it, right? So since we have a list of tuples, right, these are now, you see a sequence of int, comma, int, so it's two things. What can I do with that? Well, I could make a function that takes in a tuple and then accesses both fields. Remember, tuples is _1 is the first one, router _0, little wrinkle. Or if you want to name the fields, you're going to put that case keyword in here to have that matching work. But then you can go ahead and use them as variable names. So both are possible, right? So this is the case of zip with index. You may come across this in Python if you ever use, Python iterators, for. Doesn't usually have an index. If you want index, of course, you had to do enumerate. Oops. So it's very similar to that. I'm going to do something very dangerous. I'm going to click on a link from chat during the lecture. We'll see what happens. Oh, well, lucky me, it came up in my other window. And so the suggestion from chat was they were, browsing around while I was talking. Well, how does Chisel do shift registers? It doesn't use fold, right? Okay, so let's take a look at this. I'll drag this down into this window, and we will figure it out together. So this is fun. You can watch the instructor read code for the first time. This one? Or this one? Yeah, okay, so first off, you may notice that there is a shift register and shift registers. So what's going on here? Well, the one users are going to ask for is probably this, right? And so if you want to look at the documentation here, you can see there's a subtle difference, right? So one is going to be returning a n cycle delayed version of the input signal, which is perhaps what you expect from this delay n, etc. The other one, sorry, Windows tidied up a little bit. The other one is actually a sequence, right? So these are not quite the same thing. You see, for example, this one returns type t because it's parameterized. The other one returns sequence of t. Okay, so what's this going to do? Well, it takes in some arguments. So this is a companion object doing some work here, and it is going to. This is some templating. Don't really worry about this syntax right here, but suffice to say, data is the base type for chisel things. So yeah, this is only going to apply to chisel things. And so yeah, I have an input, number of elements, and enable, which by default is true. And I'm going to call this on shift registers, and then I'm going to call last option, which basically tries to get the last element and returns as an option, and goes from there. Okay, and you can see that, for example, why did they have two of these? Oh, this one takes in the reset data. Okay. Alrighty, so how does this actually perform? Well, you can see that in this case, it's using the sequence.iterate method, which, to be perfectly honest, that's not a method I'm familiar with. We can go look that up in the documentation in just a second. So it's kind of fun. Here we are reading, learning language together. And it calls that, and then it uses the remainder. Okay, so let's go ahead and search for Scala seek iterate, and hopefully we get Scala doc high. Give me a Scala doc. Or maybe I should just do Scala doc seek. Great. Okay. 13.6. That's close to what we need. Alrighty. If we go down to iterate. Oops. We will see it's not defined here. So I'm actually not familiar with that method. So perhaps I should have done the first hit, which was Scala seek iterate. It's probably inherited someplace else. So actually, if we went back up here and if I just searched on the page, it should pop up elsewhere if it's like inherited from something else? No. Okay. Well. Okay. Well, then the answer is I don't know. So this will be a fun mystery for me to look at some other time, and I can get back to you. Maybe I'll do this in the next lecture. I appreciate a good challenge. Because yeah, the code's so concise, but using operators, I don't know. And because I'm in a browser, I can't simply say, go to implementation. This is great. I will look this up and get back to you guys in time for the next lecture and perhaps put a preview on the Slack. Thank you. It's good to have things to look up. Yeah, someone suggested in the chat, what if we invite one of the Chisel developers to give their talk to explain themselves? Number one, we're very grateful for their work. And yeah, I'm sure it'll be a great explanation. So I'm sure they could do a wonderful job. But this is the user perspective rather than the developer's perspective, right? So that's what you're getting with me. You're getting the opinionated user rather than the insightful developer. Cool. Maybe I'll pause for questions on this before I move on to yet another case study. Okay, so remember our one-hop priority encoder? So remember we had some number of bits coming in, and we want to find the lowest bit that is true. That's the priority encoding portion. And the one hop means that, that only one of those bits is going to be true in our output, right? So that that's how we go about doing it. If you remember before, maybe I'll go ahead and shift the commenting around a little bit. We did this with muxes, right? So we said, hey, do this. And we basically used, in this case, recursion rather than for plus var to construct a, linear sequence of muxes such that, by deliberately choosing the order, if the 0 bit was true, it kind of had the ability to overpower it because it would, have that mux selected. And, we're just feeding in this constant here, was constant when the mux is generated, to kind of pick the right thing, right? So cool. And you see, of course, the recursive and the input is, but of course, the last call is going to have the dominance. And so if we run this, let me zoom out so you can see that text. Yeah, okay, some muxes. That's what we're hoping for. Alrighty. Now let's try and do this with the functional programming. Alrighty, so the functional programming, we're going to do a few things here. Okay, so what we're going to do, and this is, a bit of a mouthful, we're going to, take our input, which was a uint, instead turn it into a vec of bools. Okay. We're actually going to want the index. All right. Reverse fold left. In other words, fold right. The reason why this line is commented out down here, I can show you fold right in just a second. But for now, let's trust reverse does the right thing, and we're going to do fold left. Okay, starting from 0. What do we do? Well, we have what we have so far, and then we have a tuple, because remember we did zip with index. We have the single bit, we have the index, and then let's put these together, right? So, so we use the bit to select, right? If this bit is hot, we're taking this constant. Otherwise, we are going to return the amount so far. Cool. So if you're looking at this and saying, this is kind of complicated, it's not just you. Sometimes functional programming really kind of trips over itself, right? This is kind of cumbersome. But we're using the, basically fold left to perform this, iteration, recursion, whatever you want to call it, that, goes through these things n-1 times. Now, I said earlier, this reverse fold left could be changed to a fold right. It's actually not just that easy. So the language designers decided that when you're doing fold right, that, the so far should now be on the right, the second of the two arguments. So you actually need to swap the order, and that's what's going on with these. The mux part is the same. It's just the arguments on this side are swapped when you go fold right. This is also going to produce the correct hardware. It doesn't need the reverse, so perhaps that would, save a step. Yeah. So that would be what fold right. So here's an example of where, you can see actually, fold right technically would be the right thing. Otherwise, we use fold right so rarely. Maybe if you, would prefer to just kind of shoehorn fold left in there and reverse it, that's okay. Normally I would tell you, oh, don't reverse things you don't need to, because that's a lot of, wasted computer memory. But as I said earlier, right, because it's going to be hardware someday, if you're worried about the software execution of it, that's probably a sign your hardware's going to be really, really big, right? So it's one of those things where it's technically inefficient, but we'll live, right? I would choose readability. And this is one of those cases where, with functional programming, we did it, but we chained together a lot here, right? So this is getting pretty dense. Even though the line count's nice, right? You can ignore the comments. It's still, it's still pretty heavy. I'm not sure this is as clear for readability, so we can have some debates. And as always, it would be responsible of me not to point out that this is in the standard library, and you can just do that. And so, even though I keep reinventing the wheel, so to speak, as pointed out, the shift register, a lot of things are in the standard library, and you should use that. And just one more time, maybe it's kind of a reminder for those who've forgotten the behavior of this component. I'm going to go ahead. Actually, I can use that one just fine. And let's turn on our printf. And instead of printing the Verilog, let's actually run a little test case, right? And actually, it's more clear if I do it this way, perhaps. You can see, okay, here we are iterating all possible scenarios, 0 through 7. And we can see what the one-hot priority encoding of it is. Okay, so 0, well, there's nothing in code, but taking the least significant 1 bit. Okay, so this point is pretty clear. Here there's 2 1s. Which ones are going to choose? The least significant one. Here's also one with 2 1s. It's choosing the least significant one. Here's one with 2 1s, the less significant of the two, right? So that's what it's choosing. Cool. Other questions? Okay. All right. Well, let's try another case study. Let's go back to our crossbars. Remember, our crossbar is something we did when we were talking about arbitration, where you have some sort of, this is like a network component, right? You have some number of input ports, some number of output ports, and you're trying to send messages, right? So our messages have both a destination address, it's a number on one of those output ports is numbered, and then there's some data we're trying to send to payload, right? And then our I/O for a whole crossbar, right? Well, we have num-ins inputs and num-outs outputs. These are all decoupled. The reason why they're decoupled is because, both parties involved, both the sender and the receiver, may not be able to participate, right? The sender may not be sending data every cycle, so they may not set valid to true, they may not be sending the data. The receiver, meanwhile, may not be ready to receive, right? In the case of this crossbar, if multiple senders or multiple input ports are sending to the same output port, guess what? We use those arbiters to select only one of them is going to win. And so perhaps one of those inputs is not going to be allowed to send a message because the output port is busy because someone else is sending to it. Or maybe it's busy because the output port just isn't ready. So these are all decoupled, right? These output ports are decoupled, the input ports are decoupled. It's all parameterized. This part's nice and easy, right? Just writing this interface. You can imagine there's a lot of wires here, but in Chisel, oh man, that's nice and simple. Typed. Great. Using patterns we'll recognize, people know what decoupled means, people know what vec means. We're rolling, right? So this is cool. Okay, so now for the next stage, we're going to take that massive body, which last time we did all with for loops, and see if we can't start applying functional programming. And so I'm going to do it in kind of multiple phases. I'm going to do it just the inner loops, and then one level on top of that, and then we're going to test it. Okay, so for example, right, we have kind of these 2 major loop nests, right? So for every input port, what do we need to do? Well, as a reminder, we have an arbiter per output port, right? So we make a bunch of arbiters for the output ports. And so what do we need to do? Well, for the input ports, for each input port, we need to collect all of the readies from the arbiters, right? So remember, it's kind of that all-to-all connectivity where for every input port, it needs to connect to the readies of every, for its corresponding subport on every single one of those arbiters, right? So how do we do that? Well, we're kind of using this wire vec as a placeholder to gather, right? So using this for loop to kind of gather together all these signals. And then why are we gathering them all? Well, we're reducing them, right? Where if one of those is true, then we know that we're getting a ready. The reason why any one is going to be true is because, remember, these are customized per input port on the arbiter, right? So each arbiter has multiple input ports, and that input port's meant for this, crossbar input port. So if any one of those is true, that means we're doing the right thing. So, we went through all this effort to collect all of them together, and then we, order them down together. We could, of course, instead do that all in one line, right? We can do the gathering with a map, and then we can reduce them together. So that's pretty cool. Map, reduce, right? Boom. So that's, a huge reduction in complexity right there. What about this next for nest? Okay, so for each output port, what are we doing? Well, we are connecting, so for each arbiter, we're going to go through and connect up the actual bits on the input ports to it. And we also are going to do some work on the valid. So remember, we're kind of broadcasting those input ports to every arbiter. And so to kind of indicate, is it actually intended for the arbiter? We also need to check, am I actually trying to address that? So OP here isn't so much op, it's output port ID, whatever you want to call it. And so is that input port trying to send, is it .valid, as well as is it actually destined for this particular arbiter, right? But the result is, okay, this inner loop, we're kind of doing two things. What can I do? Well, this one's not quite as flashy, but I could use a for each, right? So in this case, we're worried about making connections. Use a for each, right? Example, the other case at work, right? And in this case, we are doing a for each on something we zipped, right? So we took the arbiters and the input ports, we zip them together. So we have an arbiter input and a zip input. And then now that we have these two, we can just kind of, do the connections directly. So in this case, we actually don't even see the indices, right? The indices for these things are kind of hidden here. We kind of had, using the for loop to kind of materialize index space, and then we were, using it to index into things. We index into things here for the arbiter in the first place, and then, this implicitly kind of has the right elements being passed around. So you actually need to materialize those indices. So yeah, that's pretty cool. So if we go ahead and, run this, it will not yell at us. Great. At this point, I would say functional programming is looking pretty good. This line's starting to get a little heavy, but because I would argue, this is a very simple use of map, kind of just grabbing things, and this is a very simple use of reduce, just combining things, that perhaps this line is not the craziest thing. And this one, yeah, you're using a for each to kind of tidy stuff up. Some people really like using the for loops. That's fine. In this case, there's not a huge line count reduction. There's a little bit of personal preference here and trying to think about not just what you like as a programmer, but also what might be fastest and easiest for somebody to read later on. One benefit actually to for loop style is sometimes it's easier to modify this, right? If you want to go ahead and toss another line in or something, versus here I might need to mess with my zip signature and my case signature or something. So there's sometimes some benefits to doing it the other way. But like I said, it's a fun class. We're going to try things out, perhaps go too far, and then we know why we want to not go so far next time. Cool. Alrighty, so now we did just the inner loops last time. Let's crank it, right? So right now I've commented, I have the original version. Okay, so before, if we remove the prior stuff, it used to be two loops, remember? And we, with our functional programming, we collapsed the inner loop into a functional statement. So yeah, now it's just one loop of functional statement. So yeah, it's way simpler. That's pretty cool. How could I avoid the need for this functional statement? Well, I could, so this for statement, I could do that with functional programming by doing a for each. Now in this case, I can do a for each because I want the side effect of making connections. Great. I'm actually going to need to hang on to the index, right? And the reason why is we kind of need the input port kind of in both cases, right? There's this, even though it's called in, this is, remember, it's originated from the arbiters. This is input port on the arbiter versus, input port on the thing. And we want to make this kind of connection between these two different ranges, so to speak. And so, yeah, we're actually going to need to hang on to that index. So here we zip of an index to get the index available to us, and then we did a for each because we want to iterate. We only care about side effects. This one, to be honest, maybe too far, right? But we did it. We did functional programming, no for loops, but maybe we went too far, right? Okay, then what was the next loop? Well, after all the collapsed simplifications we did, we had this nested loop. Instead, we replaced that with functional programming. We have this. Okay, so now we have a for loop across the outs, and like above, there's some places where we kind of need that OP, so to speak. We see we kind of appear as both here. In this case, indexing into the arbiters. In this other case, indexing into the outputs. These are different collections being addressed by the same index. We're going to kind of need to materialize that index. So we're once again forced into, unfortunately, having to do another zip with index. So zip with index is fine, but sometimes it makes total sense why you need to do it, but it also adds some complexity, right? So we have a zip with index on a for each, which internally has size of for each. Once again, perhaps we went too far, right? I mean, this is going to work, but perhaps we went too far. But it's fun to kind of try it out and see what it's like, right? And although we can't see it, I think this is going to, run without issue. To go ahead to the next slide and, run this over a test bench. This is a test bench from before. So, we're trying to send from 2 to 0 or from 1 to 1. You can see it's alternating because, we're using a round robin arbiter, but the kind of key point is it works, right? Cool. So maybe I'll go back here while we take any kind of questions or comments, discussion points, etc. Okay. So this is my closing slide on this. Here we are, kind of very practical engineers trying to build robust, reusable, efficient hardware generators. We're not forced to use functional programming, right? Functional programming is available to us in Scala. It's not the only way to use Scala, right? We have for, we have var, we have recursion. What's kind of deal here, right? Well, I say if we use it well, we see the benefits, right? We can do a common pattern, and rather than kind of reinvent the wheel of doing map with a for loop, we can just do map, right? And so when we kind of identify common patterns, reduce line count, reduce complexity, both to read and to write, that's great. Our goals are to simplify code, improve readability, reduce chances of bugs. These are all good things, right? I just saw on the prior slide, sometimes you're doing something that's pretty complicated, and when handling really complicated problems, in this case, kind of use a very specific all-to-all connectivity between these various arbiters and ports, maybe it's nicer to kind of take it very incrementally, piece by piece, kind of a simpler way of for loops, right? Perhaps, right? But we can see, if you really kind of start chaining together these operators, it can get unreadable. And I have come across plenty of pieces of Scala or Chisel code, just 4 functional operators on a line, 5 functional operators on a line. Ooh, it gets real hard to read, and you kind of spend a lot of time parsing it. And yes, it's one line, but the reader spends 10 minutes reading that one line, right? So it can definitely be overused. Like I keep saying in this class, in this lecture, try it out, have fun, but understand you're gonna see what overdoing it's like. And more often than not, what's gonna happen is when you're writing it, maybe you think it's not too much of an overdone, but come back to that code 6 months or a year later and you forgot what it did and what each step of that functional pipe is doing, then you're gonna see that. So my advice is, number one, limit yourself to 1 to 2, maybe 3 in some extreme cases, functional operators per line. And ask yourself, okay, if I did this instead as a simple for loop or even with recursion, would that be more clear or easier to get correct? Another detail is, even though you can have multiple lines, these function literals, these lambdas, if you have multi-line lambda, there's probably a sign you should just make it a named function, right? You can make it a named function, write it out clearly by naming, give it a more clear intent for what the arguments are and what it does, what the name of the function. Do that. Cool. Okay. So with that, any last questions? Cool. Okay. Well, with that, have a good day, folks.